Hi everyone, welcome back for today's class. Today we will discuss another application of Gauss's law. Last class we discussed how to find out the electric field near an infinitely long uniformly charged wire. Today we will discuss another application to find the electric field near a uniformly charged thin plain sheet. Okay. Electric field near to find the electric field near a uniformly charged thin infinite plane sheet. So we have to consider a plane sheet, infinite plane sheet. It is uniformly charged. I am drawing a small section of such a plate, such a sheet. See, this is a thin sheet. Imagine that it is infinite. Okay, infinite area, thin sheet. It is uniformly charged. So let Q be the charge on it. See, these are the charges on it. It is an infinite plane sheet. Remember, the sheet is very thin. A charge Q is distributed over its surface uniformly. Okay. Here I am defining a quantity, surface charge density. Surface charge density is the charge per unit area. Let sigma be the surface charge density. So how it is defined? Surface charge density, sigma Q by area. So what is sigma? Surface charge density. It is the charge per unit area. From this equation, you can find out the charge, sigma A, charge on the surface. So what is the unit of surface charge density? It will be charge per area, coulomb per meter square. Okay, SI unit of surface charge density is coulomb per meter square. So you have to consider a uniformly charged plane sheet. We assumed that sigma is the charge per unit area. Okay. And I am finding electric field near it. So imagine a point near it. This point is P. Okay. So imagine a point P near it. And ds, consider a small area ds around the point P. Since charge is positive, you know, electric field due to the charge is in this away from the positive charge. This is the direction of electric field. And to apply Gauss's law, you need a closed surface. So you imagine a closed cylindrical surface in this way. Okay, it will pass through the sheet to an equal distance on other side. So the surface of Sir, this cylinder is the Gaussian surface. This cylinder is the Gaussian surface. Okay. Why we are imagining a cylinder there? Because to apply Gauss's theorem, we need a closed surface. When you consider this cylinder, some charge is enclosed inside. Okay. See, in this circular area, charge is enclosed. So in this cylinder, some charge is enclosed. So we can apply Gauss's theorem to that cylinder, right? That is why we are considering the cylinder. Instead of cylinder, you can consider a cuboid also, no problem. Gauss's theorem is independent of the shape of the Gaussian surface. We already learned. Okay. Here also, this cylinder has two types of surfaces, flat surfaces and a curved surface. Here, electric field is along x direction only. See, flat surface area direction is this way. Electric field and flat surface area normal are in the same direction. For the flat surfaces, the area vector and electric field are in the same direction. So angle between them, theta, is 0. You consider other surface also. Electric field in this way, normal to the area, same direction. When you consider the curved surface, normal area, normal, if you consider a small area on the curved surface, normal is in this way. Electric field is, see, direction is 90 degree, right? Angle between E and dA over the curved surface is 90 degree. Okay. You see that electric field is along x direction only. So there will be flux along x direction. Along y direction, there is no electric field. So there is no flux along y direction. Imagine, keep it in mind. Okay. Now I can apply Gauss's theorem. What is the statement of Gauss's law? Closed integral E dot ds. ds. Here I am taking area, not as area, dA equals q by epsilon 0. Here also closed integral can split it into, closed integral means you have to consider full surface area of the cylinder. I am splitting into two. Curved surface E dot ds plus integral flat surface E dot ds. It is not ds, dA. I took A as area. So you write dA only. dA. Here also dA. Equals q by epsilon 0, right? Then, you know, A dot B is AB cos theta, you know. So we can simplify as integral curved surface E dA. See, over the curved surface, what is the angle between E and A? 90 degree, cos 90. Plus integral flat surface E dA over the flat surfaces. What is angle between E and dA? It is 0, cos 0 equals q by epsilon 0. Look at the first term, cos 90 is 0. So we can write it is f flat, integral flat surface E dA equals q by epsilon 0. Now the electric field is constant at the point P into integral dA, right? Flat surface equals q by epsilon 0. See, what is this integral dA? See, dA is a small area at the center of that cylinder, right? That cross-sectional area A. When you take integral means total surface area of the sheet. But remember, for this cylinder, there are two flat surfaces. So what will be integral dA? It will be 2 into A. If you take integral dA, that will be the total area of the sheet, right? But into 2, because there are two flat surfaces for the cylinder. Or the sheet also, there are two surfaces, right? One this and the other on the opposite side. So what we can write? Integral dA as 2A. What is AA? Area of the sheet. Integral dA equals 2A. So what will be the electric field intensity? E equals E into 2A equals Q by epsilon 0. E is equal to Q by 2 epsilon 0 A. Also, you know, Q is sigma A in the beginning of the derivation. Sigma is charge density, charge per unit area, surface charge density, charge per unit area. So what is Q? Q is sigma A by 2 epsilon 0 A. You can cut A. So what is the equation for the magnitude of the electric field near the sheet? Sigma by 2 epsilon 0. In vector notation, vector form, what will be the equation? E bar equals sigma by 2 epsilon 0 I hat. Or we can write n hat. I hat or n hat. N hat means normally. N hat. So this is the equation for the electric field near a thin uniformly charged plane sheet. So in this equation, you saw that electric field is not depending on R distance. Sigma by 2 epsilon 0. Sigma is a constant. Epsilon 0 is a constant. So electric field is constant on both sides. It is not depending on the distance. Okay, remember this point. So if you plot a graph between electric field and distance, what will be the shape of the graph? It will be a straight line parallel to the x-axis because it is independent of distance r. Graph between electric field and the distance r. Okay, so how will be the graph? Electric field you take along y-axis, r. See, equation E is sigma by 2 epsilon 0. There is no r, so it will be a constant. So graph will be a straight line. Okay. And we can consider a special case. If the sheet was thick, what would happen? See, here we consider a thin plane sheet. If the sheet was thick, what would happen? You know, for a thick sheet, charges will be on both the sides. Thin sheet means charge is at the center of that sheet only. Only charge is common to both the surfaces. But when you consider a thick sheet, charges will be on both the sides. Then you have to multiply by the electric field equation with 2. So case 1. For a thick sheet, if you consider a thick sheet, the charges will be on both sides. Therefore, electric field intensity will be sigma by 2 epsilon 0 into 2. So you get sigma by epsilon 0. So thick sheet, that means it is a conductor, right? So this is the electric field near the surface of a conductor, sigma by epsilon 0. Okay. So this derivation is very important for examination point of view. Okay. So what we have seen that electric field intensity near a uniformly charged thin sheet is independent of the distance on either side, right? What is the equation for the electric field intensity? Sigma by 2 epsilon 0. That is for thin sheet. When you consider a thick sheet, what is the equation? Sigma by epsilon 0. Okay. So in vector notation, we can write E bar equals sigma by epsilon 0 n hat. This is the special case. Now we can consider one more case. Suppose there are two thin sheets arranged parallel to each other. Then what will happen to the field between the sheets? Okay, let us see. So as a case 2, electric field between two plane charged sheets. Okay. So we consider two sheets. This is one sheet, two parallel sheets. This is one sheet. Okay, it is thin sheet only, and there is a charge Q. Suppose charge density, surface charge density of this sheet is sigma 1. And I am placing one more parallel sheet like this near it. This is also, say, positively charged. This charge density is sigma 2. So take two thin charge sheets. Charge densities are sigma 1 and sigma 2. They are placed parallel to each other. You know, we can consider three regions. See, this region 1. This is region 2. This is region 3. You consider these three regions and choose a point on the left side of first sheet. See, at this point, on the left side of the first sheet, electric field intensity is E1. That is directed towards left because electric field is away from positive charge due to the first sheet. So in the same way, the second sheet has also electric field intensity at this point. Say this point, this left side point you take as P1. So at the point P1, there is also field due to the second sheet. What is that field? E2. So in this region, on the left side, there are two fields. What are they? I can write E1, electric field in the region is E1 plus E2. What is E1? Sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0. This is 1 by 2 epsilon 0 into sigma 1 plus sigma 2. What is the direction? Directed towards left. So this is the electric field in the left side. Now you come to the point in the middle region between sigma 1 and sigma 2. See, there is a point P here. You point P2, you take it as P2. See, At P2, electric field due to the first charge will be in this direction, away from the first sheet. Electric field due to the second sheet at the point P2 is opposite in this way, because electric field is always pointing away from the charge sheet for positive charge. Positive charge, it points away. So in the region 2, these two fields are opposite in direction. So in the region 2, what is the net electric field? I am writing as E2. That is E1 plus E2. What is E1? Sigma 1 by 2 epsilon 0 plus E2. E2 is directed towards left. So I write minus sigma 2 by 2 epsilon 0. Why that minus sign? Because it is directed towards left side. So we can write 1 by 2 pi epsilon 2 epsilon 0 sigma 1 minus sigma 2. What will be the direction? If sigma 1 is greater than sigma 2, it will be directed towards right side. If sigma 2 is greater than sigma 1, it will be directed towards left. So this is the field in the region 2. Similarly, you can find out the field in the region 3. This point you take as P3. Okay. So at the point P3, electric field due to the second sheet is towards right only. Positive charge field is away. So E2 is in this direction. E1 also same direction, directed away, right? So in the region 3, what is the field? Net field E3 equals E1 plus E2. So what we can write? Sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0. So the fields add up in the region 3. So E3 equals sigma 1 by 2 epsilon 0 sigma 1 plus sigma 2. This direction is towards right. So we have seen the electric field near in the 3 regions. Now one more case we are considering. If sigma 1 is sigma and sigma 2 is minus sigma. Suppose this is the case 3. Okay. Suppose sigma 1 is sigma and sigma 2 is minus sigma. Then you see the field. What is the field in the first region? E1. You know the equation. 1 by 2 epsilon 0 into sigma 1 is sigma plus sigma 2 is minus sigma. So in the first region, field will be 0. Now what happens in the second region? What is the equation? 1 by 2 epsilon 0 into sigma 1 minus sigma 2. Sigma 1 is sigma minus sigma 2 is minus sigma. So you are getting 1 by 2 epsilon 0 into 2 sigma equals sigma by epsilon 0. Okay. Now what will be in the third region? Third region, what is the equation? E3 equals 1 by 2 epsilon 0. Sigma 1 is sigma minus sigma 2 is sigma plus minus sigma 2 is sigma 0. So we see that if you keep 2 uniformly charged plane sheets of equal charge density, equal and opposite charge density, field on the left side is 0, field on the right side 0, but there is field only between the plates. So you can create an electric field between 2 metal plates in this way. Okay, you take two metal plates, charge with the equal and opposite charges, then there will be electric field between the plates. Outside the plate, electric field is 0, that we have shown here, right? So this is a method for creating uniform electric field between two metal plates. What is the value of electric field? Sigma by epsilon 0. So this metal plate is, so this is positive metal plate, negative metal plate, opposite charge density sigma 1, minus sigma and plus sigma. First charge density is sigma minus sigma. There will be electric field in this direction. What is the electric field equation? Sigma by epsilon 0. So in this way, we can create a uniform electric field between two metal plates. Okay, children? So this application and these cases are very important. Okay, normally repeated question for board exams. So learn it well. Okay, watch the video, share the video, like and comment. Okay, so today I am stopping the class. Thank you for watching. Goodbye.